Okay, last lecture you had to work a little on solving differential equations on a tank model. Today you will, tomorrow on Wednesday you will have to work on another tank model where you have two, and there's a what's that called? A tube between them. And then we have to look at an open channel, how that works, how we can calculate on that. But before we look at it, you have this law of momentum, which is saying that if you want to find out how much energy or momentum there is, it's related to the mass and the speed. So if you have this American football, it's nice to be heavy when you want to stop somebody by running into them. Or you can be very fast and then lighter, and that will have the same effect as the heavy, slow one. But when it comes to liquids, it's a little different. If you just want to have a kind of introduction to, I think I had that one on the previous slide, Khan Academy has a nice little introduction to it here, what momentum is within physics. And then back to the track again. If you want to look at it a little on, should we say, flow or liquids, there's another rule or addition to it. Then it's not only the mass and the velocity, it's the density and the volumetric flow rate. So it's how much liquid is passing through. We have to take into consideration. So it's stated here, so the rate of change in the momentum in the system is the same as the flow rate entering a system. If you kind of imagine a surface, an area where something is entering and then it's leaving a little further back in the system. That will be an illustration soon. And then there are some forces you need to take into consideration. For example, if there's friction along the edge of a pipe or channel, then that will have an effect on what is happening with the momentum. It's kind of putting a brake to the system. So here it's summarized the flow rate in and the flow rate out, and then you have to take the forces into considerations. And that's the same which is stated here, where you kind of have the speed, and you have the flow in volume, and you have the density. So if you take the assignment, which is just a continuation of what you did last week, then in this system, instead of just having one tank, if you cut away the purple one here, then you have two tanks. So if you look at it, you have the atmospheric pressure here, you have the pressure from the water volume, and there's a balance between the pressure from here and the pressure from here. So if the pressure is higher here, your common sense will say, okay, then a flow will go through here. And that depends on how big the channel here is, or the pipe, and how hard it is to pull it through or push it through. So that's a relation which has been stated here, that the change over time of the height in the first tank and the second, and the speed, they all depend on each other with relation to the height in both tanks, and of course there needs to be an initial value. And here there's put a little more number on. What is really adjusting it is, then you have the height here of the first one, H1. Then you have a pipe with a certain area, small a here, and the length, and that gives a kind of resistance to the system. and that is stated, let's see here. So that's the length, the density, and the speed. That's equal to the sum of forces. So let's have a look at that. I won't go into details because it's not that difficult or different from last assignment you made. So here you can kind of sum up the forces. The pressure you have here is, as you've seen already previously, the pressure from the atmosphere here, P0. And then you have the height, the density, and the gravity. And then of course you need to know the surface or the area. And that's the same for F2. Then you have the friction, and the friction is what is happening in here. That's the kind of the brake to the system. And there's a fanning friction factor here. I think that's it for this one. You just need to squeeze it into Mathematica with these data. So now you have the area of the two tanks that ends up in the volume, the diameter of the pipe, and you have the liquid density. I don't know what happened here. Let's see. That helped. Like this. And you have the fanning factor, friction factor you need to include in the system. So now you just have to plot these two and the relation between them. And you have to do that for different starting values or values of the system. And you could try to solve this by using, for example, manipulate. If you look into Mathematica, you can put all the whole equation in manipulate, and then you can press on these buttons, which will be created, and you can see a difference. Or you can just make several plots and put them into a grid or table. So that was the first assignment, which is a kind of an extension to what you did last time in assignment 23. Now we are moving into a channel like this, and if we simplify it a little, we can look at a channel with water like it's a kind of square like. And of course, if you want the area, it's just the height of the water multiplied with the width. And we need something which is called the wetted perimeter, and that's if you take the area or the length from here, that's where the water is touching the channel. You need that when we are going to calculate on friction. And that's when you look at what is happening here when water is running down. There's something dragging in this volume. There's the gravity force is dragging downwards, and then you can kind of, what's that called, expand them or split them up into what is in the direction of the channel surface and what is perpendicular to the surface. So you split this vector up, and you can use that. For doing that, you of course use alpha here, and there's some assumption with that. What is small, you can assume this. Then you have some friction here on the wall, which depend on this. You need to include that. We'll come into that later. And then there is some assumption of mass balance. Nothing is leaving in a little system here. So you assume that the flow, mass flow, penetrating here, this area, if you met in this area, but the height, and then the height has increased a little here by delta H. The mass penetrating there is constant. That's what's stated here. And that means that the flow must be the same, because we assume that we can't compress the liquid. And then you have the law of momentum, that one will be zero, but we need to add the forces. And I come into that, but summing up the forces is gravity, and you have the forces here, the pressure putting on this area, and you have pressure from this area. So you need to sum that up in order to find the height. And this is just going through the relation. You can stop the video or you can look at the notebook. So this is just the relations that you assume this for what is entering, and in fact the other one is the same except for a change in speed, small change in speed. So when you subtract these two, you end up with this. And of course, if you want to find the speed of the water, if you just look at it, or let's assume you had something in the middle of the stream and you looked at that little P or something, the speed is this one. And there you need to use flow rate and divide it with the area. Then you know how much will be penetrating the area per second, or how fast it will pass through. I think that's the easiest way I can explain it. Then you need to find the change of speed. I'll come back to how you calculate that, because you need to differentiate this one. And then you end with this relation, but I'll come into that when we go, how do we put this into Mathematica. This is something which is kind of calculated by hand. And there's a little rule of thumb here, that if you want to find the pressure, P1 here, what you need is to go to the average pressure, and that's halfway down in the vertical dips, and that's what you calculate here. What did we have? Did we state it up here? No. But that's just, you take the cosine to the slope, and if you divide that with h, you have the kind of the whole vertical dips, but you only need the half to find the average pressure. And that's the same here, except for you need to add the little change in the height. And of course you can say that the flow is stated here. I'll not go into details. You need to note this, that we assume when in this relation we assume that this goes to 0. So when you multiply towards 0, these two, you assume, that's an engineering trick. I say that's a trick because I'm an agronomist, not an engineer. You assume that's 0, and that makes life easier further down. Then you of course have the gravitational forces acting on the mass of liquid in that small volume you have. The small volume, if you move delta x and the change in height, when you calculate that, you get this expression. And we need the friction, and as I said, the friction was tau, I think it's called, and you have the wetted parameter. That's, if you say there was a channel, so that's the area you have here, or the length of it, multiplied with delta x, and that gives an area. And that sums up to the friction. So you add all this up, you have the flow in, you have the flow out, and you have all the forces. And this is done by hand, so if we move on, see how can we squeeze this into Mathematica. Oh, I forgot here that of course we need to find out the shear stress. That's what it was called. And Manning has defined a little equation here, or relation, saying that it depends on the gravity forces and the density and the speed. So the faster, the higher the friction. And here's the number, Manning roughness coefficient. I have a hard time with my pronunciation, but the number is stated here. So you can see that cast iron has a lower coefficient than, for example, gravel. That's kind of logic, that there's more resistance for the water when it goes over soil or gravel. So again here we end up with this relation. I'm passing over it a little fast because the next slide we will try to put all this into Mathematica and let Mathematica do some of the job to assist us. But what is important here is that when you have a uniform flow, that means that the height is not changing or the depth of the water. And you also need to be sure that, or you can say the speed is settled, because this one is not changing. That's kind of set here, so h will not be changing, and the gravity is constant, but the speed can change. So it depends on the speed of the water. And normally you address that as a natural depth. That's where thing is kind of in equilibrium. But there is one situation where, for example, if we call this fraction the Throat number, and if that one is subcritical, you have subcritical flow when that is less than 1 here, and you have supercritical flow when it's higher than 1, and that's not a stable situation. So that will really result in that it can change fast, the depth. And that is, for example, is if water is coming into the channel with a very high speed and a low height, then the friction will slow down the water, and then the depth will increase, and you will lose energy due to turbulence. So if we say, how can we get this into Mathematica? Oh, bad spelling here. I had a little support from Valdemar, who is more used to Mathematica than I am. So please note that we use this double slash, or that's replacement rule. And we go all the way, it's replacement until the very end, if you can say in that manner. Try to reduce it. So here summarize that you have the depth, which we already seen. We need to find the average pressure, that's the halfway we have to go down. So this is just listing what we already know. And the notation is a little different, but not much from the previous. So we assume that there's a mass balance, and when we assume that, the density cannot change. So if there's a balance, you will have a common constant volume rate. And then of course we have the area we can calculate by the width and the height, width of the channel. I can hear my kids are coming home now, so I'll be a short break. So I'm back again. So what we have to do now is to find out how did we get to here, the relation in the change of speed. And we can use Mathematica to do that. So what we have the relation here is that we have the area, we have the flow rate, or the mass flow, which is the area multiplied with the speed of the water. And then we use a function you haven't seen before, eliminate, and that one will try to merge these one to one equation and get rid of A. And then we say we want to solve it, so what is the relation of the flow rate here, and it ends up being this. So it depends on what we already seen, that it depends on the mass flow, or volumetric flow divided with the area, then we get the speed. But if we want to have the change in speed, what we then need to know is what is the slope or derivative of this in relation to the height. And then we need to multiply it with the change in height too. And then you can see what happens. Then you get the relation here. You could have done that by hand, but Mathematica end up with it here. So what we do now is we try to summarize all the rules for relations. That the density is constant, that's what's stated here. The volumetric flow entering and leaving is constant. The speed entering is v, and the speed leaving is v plus the change in speed, a small change in speed. The height is the same, and this was vertical height, where you're entering the little area we are looking at, or volume, and leaving it. And that's the same with the area. And all these rules you stated is based on what you saw before. Then we know that the flow in minus the flow out will be this relation. That's already stated. And then we ask Mathematica to exchange all this all the way. So it takes all these rules and relations and try to simplify it, and you end up with this relation. And you can find that in the text, but it was done by hand. Then you have the forces due to the pressure, and there you do exactly the same as up here, with the little change that you expand it. So what you end up having is this relation, but then, as I said earlier, this little one, delta H, goes towards 0. And when you multiply that or square that, you assume that is 0. So that will kind of get rid of this part. And what you also know is that this part here is the same as 1 divided with cosine to alpha. And that is when this one is small, close to 1. So if we put that in, we subtract these two, we put in the rules, but then we also say that delta H squared goes to 0, and we say that this one goes to 1. And then you can see that relation is a lot simpler. Now we need to find the forces in the direction of the flow channel, or parallel, due to the gravity. And there you can see the relation is stated here, that this is the weight. You can see the area, and then delta X. If you multiply that, you get a volume, you have the density, and then you need to see what is the forces parallel to the channel surface. Then you have the friction forces, the same here. So now we end up with the big solution, with hopefully the same as when it was done by hand, where you have flow in minus flow out. You have the pressure forces, you have the gravitational, I can't say that word, gravity forces, and you have the friction forces. And that needs to be 0, as we stated earlier. So we solve that with regard to delta X. We simplify it as much as possible, and we ended up with this relation. It's a little different than if we go back in the slides. You can do that. Because that one was stated like this. So now we want to verify it. So this is what we ended up with using Mathematica, and this was what we ended up doing it by hand. So what we do is we make the replacement rule saying, okay, we know that the area here is the same as P multiplied with H. So we get here, we know that the speed is the same as the volumetric flow divided with the area. So it exchanges that, and we ask it to run that. It says true. So it says that these two relations are the same. So we are still on track. Now we want to take the wall shear, stress factor here into account using Manning. And you've seen that earlier. So we make a new rule here with the relation saying that this tau on the wall is this relation where you have the number, which we saw in the table earlier. We have the replacement rules here. And then we end up with the final equation. And you see I said it here, and there's one power expand here. If I don't put power expand, I end up with this relation. So it means that there's still a product. This one multiplied with this relation is not calculated. So by using power expand, it expanded and then simplified. So we get, some will say, a nicer relation to look at here. So now you can start calculate on it. If you want more information on how the relation is, then you can go to this homepage. There's a little Java calculator where you can play with numbers. But what it is that you can calculate on what happens if you have a slope, you have a volume, a height, different settings. And the red line here is the critical dips. You can go back and look at the Froude number and the relation. And then you have the natural dip. That's where things is kind of in balance. If you take an example, for example this one, if for example you have a dam, like here, if you can see that, let's put a block here. That means that water is coming out here from a very low height and will come with a high speed. And that means there's a lot of energy in the water, and this shear on the surface here, along the surfaces, that will kind of break the water, and suddenly you will end up with turbulence, and that will extract energy out of the system. That's the same as removing or reducing the speed, and the water height will increase and gets closer and closer to equilibrium. You can read these relations here. It's not my strongest side. The hydraulic jump is explained here. There's also a nice little YouTube showing it, explaining what's happening, but it's kind of what I said, that you can use this turbulence to, or if you put a dam or big stones in a stream, you kind of pull out the energy of the water and reduce the speed and increase the water depth. You can also use it for mixing. Here saying that you can mix chemicals, but it could also be oxygen, and that's good for the fish. So now we come to the assignment. You have all the equations and relations from above, so you can just take it from the notebook. What you now need to do is that you need to use some initial values. You have different inclinations. You have a natural stream, you have a concrete channel. You can see natural stream is more rough in it, so the friction is higher, so that's why the number here is higher. So what you need to calculate now is the natural height, where kind of the system is in balance, the critical height for all four cases, and then after that you need to calculate and plot the depth, the liquid depth, and the elevation. So this is kind of stated down here, the elevation when you have the channel going downstream, so the height is decreasing, so it's not horizontal. And you have to do that up to 5 Ks, and then you have different conditions. You need to select H0 between the critical value and 0, for the cases you have the critical value and the natural value where it's all in balance, and then you have the supercritical here, and see what happens. And there will be cases where, you know, when you have the hydraulic jumps, things breaks down and you cannot really calculate on it. You know, turbulence is a hard one to handle. But you have to illustrate that. A nice way to do it is that if you, in the plot, first you have a plot with the critical height, the natural height, and h with like, let's see, let me go back. If you plot it like this, you don't need to include the slope in the first plot. You can do that in the second plot. You can just have it so you can see what is the critical height, what is the natural height, and then see the change in h. And then afterward you can try to plot the height as a function of, or include the slope of the channel. I think that was the first assignment. And then the last one is not that difficult because you have the whole machine up running from the previous assignment. But what is interesting is if water is passing over here and you have that height, then you can calculate backwards and say what was the height up here upstream? What is the development in it? And what you have to do that is that you kind of, when you do the calculation, you need to replace this part with this part, and that's it. It's just you kind of reverse the whole system. And then you have to calculate with these initial values, plot it again, and hopefully you will end up with a plot like this, so you can see what is the development behind the dam, or what a dam obstacle. And you do that 5 case. So I'm looking forward to see you tomorrow and see if we can break these problems together.